Once you've entered all of your building history, you can start modeling the building shell or envelope. Let's take a tour of the shell page before actually entering any new components. The heating degree day value has been carried through from where you entered it earlier. The true-up factor serves to adjust the building's heating energy load to match the energy actually consumed. And it's worth spending a few minutes on this subject now. True-up is an effective way to account for internal and solar gains, as well as behavioral effects such as keeping the thermostat higher or lower than might be considered average. All of these things cause the building's modeled heating energy to drift away from the actual heating energy consumed. A true-up factor of 65% means that the building model indicated 35% more energy was required to heat the building than was actually consumed by the heating systems. The calculation is handled within the tool by changing the heating degree days by the amount of the true-up factor. 65% is the tool default, but it can be changed, and that's the whole point of truing up. It's important to know that the same true-up factor used in your existing building energy model will be applied to your improved model as well. Once the building is completely modeled, we'll revisit the true-up factor to see how it affects the building model to match the actual heating consumption that you entered earlier in the fuel use module. Now let's add a few shell components. Click on the Add Shell component. Here's where you can name and define your existing and improved shell assembly. The effective R value is your best estimate on how that shell assembly that you're modeling is operating. Exposure factor is how closely that shell assembly is linked to ambient temperatures. So an exterior wall would be 100% exposed to ambient temperatures, but a wall to the garage might only be half of that. So again, use your best judgment and your building science expertise to enter the right exposure factor. You may also need to consider things like thermal regain in a warm attic or in a basement. Enter your proposed R value, again, the effective operating R value of that entire assembly, including the framing. And we'll give that an upgrade cost of, let's say, $10,000. And we can continue to add shell components until the building is completely modeled. Let's take a look at the shell components we have modeled so far. We have windows, walls, foundation below grade, foundation above grade, and the attic flat. We have our assembly areas, effective R values, exposure factors. Notice that on the foundation below grade, I put an exposure factor of 25%. This is because there's less heat loss to the ground that is at a constant temperature that's generally higher than average winter temperatures. Propose new R values, cost to buy and install. EUSAVE has taken the fuel prices that you entered earlier and calculated energy costs for each of the shell assemblies that you've modeled. It's also calculated the shell loads, consumption, which accounts for the heating system efficiency. We have electric heat in this building, so these loads are the same as the consumption. Generally, if you have a fossil fueled heating system, your consumption would be a bit higher than your loads. The proposed component load has also been calculated, and your energy savings for each of the components that you modeled. MMBTUs, or millions of BTUs, has also been captured. And the lifetime value that you entered earlier when you were setting up your project, this was a 20-year lifetime, that's also added up. Your simple payback, return on investment, benefit cost ratio, the improvement cost per millions of BTUs saved is an interesting way to look at the overall value of that improvement. If it costs you less to improve that component than it does to buy the energy to continue using it in the old way, then you're coming out ahead. As society moves towards carbon as a way to value energy, the tool has also calculated the cost per ton of CO2 saved. Now that our shell assembly components have been added, we can close this box just to hide the view, and we'll go up and add some air leakage. Give it a name. Add in the usual LBL climate factor requirements. We're in zone 2. There's a little map here you can refer to. Wind shielding on this building is normal, and our blower door indicates a 2500 CFM 50 air leakage rate, and we're hoping to get that down to 1000 CFM 50, and we hope that it doesn't cost us more than $1,000 to do that. Now you can take a look at your air leakage costs and savings information that the tool has calculated for you. You can see the information that you entered up here, and it's calculated the CFM natural is pre-improvement or existing conditions, ACH 50, ACH natural, CFM 50 per square foot of shell area, how much that air leakage is costing each year, what the load is, and what the consumption is. Down here you can see how the reduction in air leakage has fared in terms of cost and savings. We have similar metrics to above, but we also have some savings values as well. Now on any of these components, if you make a mistake, you can go back and edit. Let's say your cost came in a little bit higher. The shell scenario evaluation keeps track of all the totals as we enter them. Mechanical ventilation will also be installed in this building, so let's go up and add that system to our shell. You can see that there's quite a few pieces of information required to properly model mechanical ventilation systems. A good model will give you a good estimate of heating energy lost in the exhaust stream and electrical energy used by the system. If you have an HRV, you can set the efficiency levels here. If it's an exhaust-only ventilation system, then you would enter 0. Now that we've entered all of our shell assemblies, air leakage, and mechanical ventilation, we can take a look at our results. Referring back to the shell inputs from heating page, our heating disaggregation estimated 8.78 million BTUs of heating consumption. Our shell build-out, however, indicates just under 112 million BTUs. This is a pretty extreme example of not accounting for all of the details. Probably I missed some fuel usage in my billing history analysis, or perhaps I've overestimated some of the heat loss components. Let's double check by going back to the fuel use page and reviewing our inputs. Right away I can see I made two mistakes. I meant to type in 1400 gallons, not 400. I also see that I have no heating fuel units associated with this heating fuel. We'll go back to the fuel use page and edit our propane gas fuel consumption. Be sure to select the proper end use for this fuel. In this case it's heating. And we'll change our fuel units to 1400, and our baseline remains the same. Save. Back on the fuel use page, you can see that our information has been updated. We have a heating system that consumes 1,280 gallons of LP gas each year. One more thing we need to do, because our heating system was automatically set up based on our initial inputs, that heating system will have false information, so we need to edit that from 280 gallons, and we'll add in our 1,000 more gallons for a total of 1,280 gallons of propane used. We're back on the heating page now, and since we've edited two different components, we'll need to do a system-wide recalculation. At the top of each page is a recalculate button. Using the recalculate button helps to ensure that all of the numbers get dropped into the right place after you do multiple editing and deleting steps like we just did. And it looks like things are in better shape than we were. Let's check our current heating systems. We have two systems, one electric, 2575 kilowatt hours, and one propane heating system at 1280 gallons per year. Let's check our shell numbers. You can see that those figures have been dropped in from the heating page based on our update and our recalculation. And now we're ready to true up our shell again. The true up factor of 0.59 has adjusted the heating consumption from our model to align with our heating consumption from our billing use disaggregation for heating fuels. We've now successfully modeled our building, edited some components, and trued up the shell to the actual energy consumption. In the next module, we'll take a look at the heating systems and edit those as required.